puts our sun in ellipses with the sun at one focal point, and that's what the first law says. Now, the second law says directly that a line connecting our sun with an object that's orbiting it, whether it's a planet, satellite, or whatever, but a line connecting sun and planet for our purposes, sweeps out equal areas during equal time intervals. So you can kind of imagine that the area inside of each of these successive dashed um, triangle pieces, so to speak. They're not quite circular arcs because it's an ellipse, but these triangle pieces has about the same area. In fact, it would have the same area if we put our sun a little bit farther to the left over here, and then it would actually be truly at a focal point. What that means is that if you were to plot these lines as the planet goes around, these lines are much more densely packed when the planet's farther away because it's going a whole lot slower than when the planet is closer to the sun when it's going a whole lot faster. So in that case, the lines will be much more farther spread. And the third law, which is the law in which we've been doing our calculations, is that the square of the period of an orbiting object is proportional to the cube of the semi-major axis of that orbit. And that actually works whether it's a planet, stars orbiting each other, or whatever. You're going to have that same law holding. And that's something that Isaac Newton proved. And we'll come to that later in this discussion. But first, talk about some more history. Galileo. At around the same time when Kepler was making his big achievements, Galileo was making some similar achievements. So first off, I should mention that Galileo did not invent the telescope. It was actually invented at least as early as a year before he started using it by Hans Lippershey, and Hans Lippershey might have gotten the design from someone else. And it's even conceivable that there was an optician back in the 1560s who was using some primitive type of almost telescope device to make various scientific observations. But as far as we can say for sure, Galileo was the first to use a telescope to study the sky and record in detail and explain what he saw. And he found, when he turned his telescope to our moon, that it has mountains and valleys, showing that it's not the perfect world that people believed it to be, and that the Milky Way, that nice broad band of dim light that you especially see during summer and early autumn, it's made up of individual stars. And then, most remarkable, Galileo found that the planet Jupiter, the wandering star Jupiter, actually appears a little bit more like a disk in his scope, and it's surrounded by 4 points of light. And as he watched those 4 points of light over hours, he found that they changed their positions, which meant that Jupiter was surrounded by 4 moons. Now, why is this incredible? Well, one of the big arguments against any heliocentric or sun-centered models was that if Earth was orbiting our sun, as opposed to the geocentric or Earth-centered models where Earth was stationary with everything going around Earth, if Earth was orbiting our sun, then our moon should be left behind because there wouldn't be any circle around Earth for our moon to be around. So our moon should be left behind. Well, what this showed was that Jupiter is moving around either Earth or Sun without leaving its moons behind. So apparently there is no valid objection to objects moving without leaving their moons behind. Because whether you believe that Jupiter orbits around Earth or whether you believe it orbits around Sun, either way it's orbiting around something, and it's not leaving its what at the time were believed to be only 4 moons behind. Well, now we know that Jupiter has at least 67 moons, but in any case, Galileo was definitely able to see 4 through his scope. And anybody could see this. Anybody could replicate the design of Galileo's telescope and see Jupiter's moons for themselves. And in fact, you can do that nowadays. Just take a decent pair of binoculars, like even 10 by 30s would probably work. I've definitely seen them in 10 by 50s, and we used to do that as part of a night lab in astronomy class. People would look, among other things, look at Jupiter with 10 by 50 binoculars, and they would see its moons. Usually either 3 or 4 would be visible on that particular night, and they're easy to see. In fact, each one of them is bright enough such that if it wasn't for the fact that Jupiter is so darn incredibly bright, you would be able to see them just by their reflected sunlight. But in any case, yes, Galileo found that Jupiter is surrounded by 4 moons, showing that bodies other than Earth can be the center of motion. And this is kind of how they would look in a kind of small, medium-sized telescope, like the 5-inch reflecting telescope, like what we have in the back of the room. So with Jupiter and its 4 moons. Now, Galileo also discovered sunspots, showing that our sun is not a perfect world, and also that our sun rotated. He was able to track the sunspots as our sun rotated. Now, he wasn't the first to discover these. Ancient Chinese astronomers had also discovered these a couple of thousand years previously, but nonetheless, he cataloged them in good enough detail that we were able that pretty much starting with his records, we have a pretty thorough sunspot record up through the present day. And also, incredibly remarkably, in fact, I think in a lot of ways even more remarkable than his discovery of moons around Jupiter, is that Venus has phases. Not just having phases, but it has particular phases that could not be explained in the Ptolemaic system of having all of the planets orbiting around Earth. So here's the thing. This is what you see with the phases of Venus. When Venus is really close to our sun and relatively dim, when I say close, I mean close along the line of sight, you see a crescent phase. And when Venus is also kind of close but relatively bright, you see either a gibbous or a so-called first quarter or third quarter, like moon-like phases. Now, a gibbous Venus, the only way you can have the disk of Venus almost entirely lit up is if it's on the opposite side of the sun. Now, in the Ptolemaic system, the phases of Venus would have been very different because here's the thing, Venus never travels all that far from our sun in the night sky. You're only going to see it up to a few hours after sunset or a few hours before sunrise. At the present time, you see it for a couple of hours after sunset. It's that bright point of light that you see in the west-southwestern sky following our sun after sunset, and it's really nice to view right now. But Venus never is far from the sun. Why? Because Venus, now we know that Venus's orbit is interior to the orbit of Earth. So this Galileo's observations of a gibbous phase proved that Venus must orbit the sun, because if it's not all that far from our sun and you have some Ptolemaic system where it's orbiting around this epicycle on some sort of circle that's maybe inclined at about 90 degrees with respect to the line between Earth and Sun, then still the only phase of Venus that you're ever going to see is a crescent phase, because that's the only way you can have a geocentric model with Venus being never straying far from the sun. But, well, Galileo found, yeah, Venus doesn't stray far from the sun, but it has gibbous phases, showing that it's definitely on the opposite side of our sun at some points in its orbit, and this proved that Venus orbits our sun. Now, nobody really doubted this. Everybody accepted that Venus orbits the sun after they analyzed these observations in Galileo's telescope or their own telescopes that they built. This wasn't by itself what really got Galileo in trouble. I should mention, though, that just because Venus orbits our sun does not mean that Earth orbits the sun. Remember Tycho Brahe, and for that matter even Capella back in the 6th century, they thought that Venus went around the sun as well. So this was not anything incredible in those perspectives if you just think of it as different reference frames with Earth not moving. And I should really probably try to track down the scripture that says this, and I did it some years ago, but there actually are there actually are lines in biblical scripture that say that Earth does not move, that directly say that. And so the fact that or at least the idea that Earth actually is in motion was seen as blasphemy to some church officials. Now, real quick, long story short, Galileo published his works in several books, but it was particularly the one in 1632 that got him in a lot of trouble. Now, here's the thing. Galileo was publishing his works long before then. Soon after he made his discovery of moons around Jupiter and the big phases of Venus, he started publishing his work. For the most part, the Catholic Church at the time supported him. But some of the lower level church officials were against him, like for example the Dominican friars. They were to a large extent against him, and they wanted to drum up some reason some reason to kick Galileo out of the church, some reason to excommunicate him, because he kind of rubbed them the wrong way, and Galileo was not one to tolerate fools lightly, and so that rubbed them the wrong way, and they wanted to find a way to get him kicked out of the church. So they tried to drum up some charges against him around 1616, and he ended up getting called before the Pope. And the Pope, thing is, was actually Galileo's friend. And the Pope said that, well, I know about all of this stuff that some of these lower level church officials are trying to raise against you, but I support you, and as long as I am alive, you will have nothing to fear from any of them. Well, it turned out that wasn't long enough. That pope died around, I think, 1623, and then there was a new pope. Well, it turned out that new pope was also a pretty good friend of Galileo. And you might say, well, why should there be a problem here? Well, here's the thing. The new pope, even though he's a friend of Galileo, and he was one of Galileo's biggest supporters back in the 16 teens when the lower level church officials were trying to go after him, he did not, nor did the previous pope, advocate a heliocentric worldview. They still advocated a geocentric worldview. They thought that Galileo's scientific contributions were significant and important, but they still advocated the idea that Earth is not moving. They realized, yeah, Venus probably goes around the sun, but they figured that Earth itself is not moving. But Galileo insisted that Earth is also definitely moving, and he ended up publishing works about this and basically showing quote, proof that Earth moves in his 1632 book, Dialogue Concerning the Two Chief World Systems. And his supposed proof was based on the fact that we have 2 high tides per day. Now, the Catholic Church at the time said, no, that's wrong. The reason that we have 2 high tides per day is because of influences of our moon. They didn't exactly understand things like tidal forces and stuff like that. That would have to wait until Isaac Newton came around. But they realized the apparent coincidence between our moon's position in the sky and the tides, and they realized that the 2 high tides per day, roughly 2 high tides per day, were because of our moon. It had nothing to do with Earth's motion. And that's correct. Even 400 years ago, they got this correct. Galileo was wrong on this, and it was his insistence on this particular supposed proof, this false proof of Earth's motion, supposedly sloshing around the ocean water due to Earth's motion around the sun while rotating, which is actually disproved by Galileo's own physics that he helped develop, that really got him in trouble. And the final nail in the coffin was in this book where the Pope had told him ahead of time. Galileo asked the Pope for permission to publish this book, and the Pope granted it. But the Pope said that you need to make it clear that you are not advocating that Earth is actually in motion. You can advocate that the mathematical data work well if Earth is in motion. In other words, you can advocate that this model works as a good predictive model of things, but you should not advocate that it is actually true reality. Well, so Galileo published his book, and basically it was an argument between, it was seen as a play, as an argument between a person supporting Earth in motion and a person named Simplicio against the Earth being in motion, and then a supposedly neutral judge judging the 2 arguments. And of course, the judge judged the argument in favor of the person arguing in favor of Earth's motion. Now, the thing is, Simplicio, at the end of the work, said, okay, this sounds all well and good, but one cannot necessarily conceive of the true nature of the Lord, and the Lord could have created the universe in such a way such that all of this would appear to be the case but not actually be the case, which were the Pope's words coming right out of the simpleton's, Simplicio's, mouth. This enraged the Pope. He had been Galileo's friend through thick and thin, and suddenly Galileo was stabbing him in the back. And that by itself might not have gotten Galileo in serious, serious trouble, other than the sad breaking of a friendship in, say, the time of Copernicus, when this probably would have just been put as a footnote at the beginning of the book that this isn't supposed to advocate anything real. But this was the time of the Counter-Reformation. The Counter-Reformation was really strong here. There was a lot of politics going on in this. So the Pope, who had a lot of his minions kind of turning against him at around this time, felt like he was under a lot of pressure to make a very strong stand for the church, so he had to really come down hard against Galileo. And so he summoned Galileo to the Inquisition. Galileo was forced to recant, and he was placed under house arrest for the rest of his life. Now, a lot of this house arrest wasn't in too terrible of conditions. For the first year or so, around the time when he was called to the Inquisition, he was actually treated really well, but nonetheless, he was banned from any further publications of his books after this point. So it really says a lot about a lot of the stuff that was going on in church politics at the time. Galileo, by himself, he was generally highly respected among the upper-level church officials, but when he finally ended up stabbing the Pope in the back, so to speak, that got him in a lot of trouble. Now, it's very interesting what the Pope said at the time, that God could cause things to appear in very different ways, and such that all measurements would result in these appearances when things are actually very different. Because nowadays, you actually hear that very same argument often laid out by people who are against the idea of biological evolution, which scientifically has been completely proven. I mean, mitochondrial DNA sequencing is actually used to derive lineages. In other words, it says, okay, take this animal and this animal, how many generations ago did they share the same mother? Because the mutations in the mitochondrial DNA happen at about the same intervals, so you can actually figure out how many generations ago and then make an estimate about how many years ago these animals had the same mother. And it's been used to derive lineages in a number of cases that are eventually confirmed by fossils sharing the characteristics that are predicted by the lineage that's derived. Because when you end up deriving one of these lineages, even if you haven't discovered the animal yet, the traced back mitochondrial DNA sequencing tells you what the animal should look like. So then you end up looking for the various fossils, and then you find those various fossils at about the level in the strata that you would expect. So it's really quite a remarkable finding. But what some of these people are saying, who do know the science, they say, well, yeah, this is all well and good. Everything scientifically checks out, because eventually they're forced to do that once they end up having to gain enough background in the various sciences to do this. But eventually they say, well, but nonetheless, maybe God planted these fossils here or made these changes in the mitochondrial DNA so that it has the appearance of a very, very old world with quite a lot of stages of biological evolution. And it's really exactly the same argument that the Pope tried to use against Galileo 400 years ago. But the question then comes back, well, why would God trick us? Because I mean, in fact, especially when you really get into quantum mechanics, you find that if something cannot be measured, then it's not really scientifically viable. So what you have in terms of what can be measured, in principle at least, really is how the world is when you really get down to it. And that's what modern science especially is showing. And we think that quantum mechanics might have a proof of that. If it's not, well, we still consider it to be quite obvious that, well, the simplest explanation, given everything else being equal, is going to be the best one, Occam's razor, in other words. So it's definitely a lot simpler, considering all of the facts, to realize that we have this general sequence of events that occurred, as opposed to God apparently tricking us to test the faith of people in certain denominations, to something that's very different, especially when we keep finding things that are more and more consistent with the present paradigm on that. So, ending with this last thing about Galileo, who really helped to get science into a lot of its modern ways of thinking, so going by a famous song and everything. Now, something else that I should also mention about Galileo. He did not convince the scientists of his time that Earth actually travels around the sun. He convinced everyone that Venus definitely travels around the sun, but not Earth. And again, Galileo got in trouble because, well, really he was backstabbing the Pope when Kepler was saying the same things at the same time, without backstabbing the Pope or being particularly abrasive to church officials. So Kepler actually ended up being the one who convinced people that Earth goes around the sun, because even though Galileo gave this incorrect proof of the sloshing of Earth's motions when it was actually caused by our sun giving our moon giving 2 high tides per day. Kepler, through his third law and the second law, particularly when the latest set of data were published around in the 1620s, it was actually Kepler's data that convinced people in the broad scientific community that Earth goes around the sun. In Copernicus's time, nobody was convinced. We didn't have any parallax. There was nothing to convince anybody that Copernicus's model was any better than Ptolemy's model. It took the observational data, the very precise observational data begun by Tycho Brahe and extended by Johannes Kepler, that convinced people that Earth actually does go around the sun. In terms of final proof of that, that wouldn't occur until the 19th century, when actual parallax motions of stars were found by Bessel and others in the 1820s and 1830s, and then by Foucault's pendulum experiment, I think it was in the 1840s, that showed that Earth actually does rotate, that it absolutely rotates. And that was the final proof. But before that, everybody was pretty convinced, mainly because of the data of Johannes Kepler. Now, this leads to some philosophical implications. Earth is no longer at the center of the solar system. So is Earth really as special as we thought it was? In fact, now we realize that, well, our Earth is one of a number of planets in the solar system, and a lot of these planets contain so-called solar systems of their own. I mean, the 4 Galilean moons of Jupiter are really rich and diverse. Saturn has a moon called Titan that has a whole lot of organic matter on it, could potentially, who knows, maybe support some type of life as we don't know it. It has another moon, Enceladus, that maybe even does have some life as we know it under its surface with its oceans. Same with Jupiter's moons, Europa and Ganymede. So are we really all that special? And this is one of the big things that the Copernican revolution led people to question. So just going through with a real quick tour of our solar system, here we have the innermost planet Mercury, which bears a superficial resemblance to our moon, and then Venus, the hothouse of the solar system, with its runaway greenhouse effect, the hottest planet in the solar system. And then, of course, we know about Earth. Here's Mars with its nice polar cap up here, and the Valles Marineris Canyon system, one of the most extensive canyon systems in the solar system, many times larger and deeper than the Grand Canyon. And then Jupiter with its nice great red spot, and here's its innermost major moon, Io, which has it's the most volcanically active object in the solar system. And I think this is most likely Ganymede, which is the largest moon in the solar system, larger than the planet Mercury, at least in terms of direct size. And then some close-up images, Io, Europa, Ganymede, Callisto, the 4 Galilean moons, the same moons that Galileo found in his telescope. And then Saturn, and you can see some of these specks of light. These are some of Saturn's moons. And then its biggest moon, Titan, which is about the same size as the planet Mercury, slightly larger, I think. And also has an atmosphere that is even denser than the atmosphere of Earth. And then kind of a close-up of some of Saturn's moons. This isn't a real image. These were pasted on top of other images of Saturn, but they are pretty much how these moons would appear to our eye. Look at this, the so-called Death Star moon with the Herschel crater. The moon's called Mimas, and the crater was formed by an impact that almost busted that moon apart. And here's another close-up of Titan, and this is either Mimas with its Herschel crater or Tethys, which has a similar so-called Death Star crater called Odysseus. But yeah, notice that nice haze of an atmosphere around Titan. And then Enceladus, which has water ice geysers coming out down here, and we realize now that there's an ocean, or at least a sea of liquid water under its surface right here that's being heated by a combination of tidal forces and leftover tidal forces from previous interactions with other moons. And then the planet Uranus, which was actually discovered after Isaac Newton died. But it was discovered serendipitously by William Herschel. And then Neptune, which was discovered based off of predictions from Newton's law of universal gravitation, a very important discovery because people thought, based on the orbit of Uranus, that Newton's law of universal gravitation, some people might conceive it as being wrong. Well, in truth, nobody really thought that. What they thought was that, okay, let's assume that Newton's law of universal gravitation is correct because it has worked so well for so long, so we need an augmenting hypothesis to explain these strange motions of the planet Uranus. Well, that augmenting hypothesis is there's another planet out there that has not yet been discovered. And based on the motions of Uranus, people were able to predict where in the night sky that planet should be, and then in the 1840s, that planet was discovered, Neptune, and the largest of its moons was discovered a few days later. And as you know, we have a whole lot of other solar system bodies out there as well. And then, beginning in the 1990s, we started to discover other planetary systems around other stars. And we now realize that there are lots and lots and lots of planets in our galaxy, including quite a number of planets in these so-called habitable zones around their stars. In fact, this number 14 needs to be updated by about twice that amount, because we've just over the past few weeks there has been the announcement of discoveries of more of these objects. But lots of planets around in the habitable zones, in other words, in the regions around their stars where you would expect any water to be liquid. So these are some really remarkable discoveries. And they're really continuing the Copernican principle that we are not necessarily special, at least in terms of our existence, our location, or anything like that, because now we're finding that there are lots and lots of these other worlds out there. So just an artist's image of something like this. Now, this heliocentrism is still this idea that the sun is the center of the universe. Well, after we realized that that our sun is the center of our solar system, we eventually realized, after still a couple more centuries, that our sun is just one of many, many stars that are orbiting around the Milky Way. Even during Isaac Newton's time, we didn't realize that all these stars were orbiting around something. Isaac Newton thought that it was a miracle that there were all these stars in the night sky that did not change their positions. In fact, he thought that God was literally correcting the universe at every instant to make sure that those stars didn't change their positions. Well, keep in mind, even though Isaac Newton was a genius, religious predictions made hundreds of years ago do not really bear much fruit because we didn't have a lot of the observations then that we have now. So in other words, Isaac Newton, while one of the greatest scientists of all times, did not have anywhere close to the knowledge that we have in the present day due to the people who have descended intellectually from Isaac Newton and their proteges as well. So we realized that, yes, our sun is just one of many, many stars orbiting around our galaxy. Now we realize that there are about 400 billion stars in our galaxy, and probably a good 100 billion planets, with probably at least 10% of those being in the habitable zones around their stars. Not to mention other rogue planets that have been ejected by gravitational interactions from their solar systems that are just wandering around in interstellar space as nomads without any stars to orbit around, without any homes. And so it's just a really rich place out there. And then, in the 1920s, we realized that the so-called universe, which was our Milky Way galaxy, well, that's not all that special either. First, the so-called Andromeda Nebula was realized it was actually a galaxy because we started seeing very familiar-looking stars there that had very familiar brightness patterns, and from that we were able to realize, okay, these stars actually have this brightness, therefore we can figure out the distance to the Andromeda Galaxy based on the apparent brightnesses of these stars that are like ones that we have already cataloged. Well, it turned out those stars were a little bit different from ones that we had already cataloged, which means that our distance estimations to the Andromeda Galaxy were wrong. It turns out it was actually many times farther away than what we originally thought, but even what we originally thought made us realize that our Milky Way is not alone. And then astronomers, especially Edwin Hubble, started discovering that more and more of these so-called spiral nebula are actually island universes, just like our own Milky Way galaxy. And some of those are many times bigger than the Milky Way galaxy. Now we realize that there are about 120 billion galaxies in the visible universe, give or take. That's a serious estimate. If it's within 50%, most astronomers will probably be pretty happy. But nonetheless, many, many billions of galaxies, each with many billions of stars. Some of them with trillions of stars. For example, the Andromeda Galaxy has over 1 trillion stars, we think. And the galaxy at the center of the local supercluster of galaxies, called M87, that's the name of the galaxy, it has probably several trillion stars. And who knows how long some potential alien life forms could have existed and then vanished on some of the planets that might have orbited some of those stars. It's a really old galaxy. So here's a so-called map of our Milky Way, and if you were looking at it from above, this is an artist's image. Of course, we have not sent spacecraft far enough away to take pictures and send those pictures back to us or anything. But yeah, here would be our sun, and have a lot. We're in kind of near one of the spiral arms of our galaxy. And then here's the Andromeda Galaxy, which we've discussed before. And see this and this. These are a couple of dwarf galaxies that orbit the Andromeda Galaxy. There are a whole lot more that you just can't see here because they're too faint. Our Milky Way galaxy has at least a couple of dozen little dwarf galaxies orbiting around it, which I just think is really cool. And then here's another nice spiral galaxy that's relatively nearby, but it has twice the size of the Milky Way galaxy. It's a truly giant spiral galaxy. And then there's that galaxy M87 that I mentioned before that has trillions of stars and a black hole at its center that has a mass 6.4 billion times the mass of our sun. How do we know that mass? Well, we're going to talk about that soon, because that's the type of thing that you guys should be able to calculate by the end of this unit. Now, not only did Edwin Hubble discover that there are lots of other galaxies other than the Milky Way, he also discovered that, by and large, those galaxies are moving away from us, and they're moving away from us at a rate that is proportional to their distance from us. And funny thing is, general relativity predicted already 10 years previously that the universe could not be static. In other words, the general relativity predicted that the universe must either be in a state of collapse right now, or be expanding from some moment of creation, which is what astrophysicists called the Big Bang back in the 1920s. They simply called it the moment of creation. So when astronomers realized that the universe actually does seem to be expanding, in other words, that this actually seems to be an expansion of space itself carrying the galaxies along as dictated by general relativity, we realized that the universe actually did have a moment of creation at some time in the past. Now, in the 1920s, that moment of creation was a ridiculous, well, nowadays we realize this to be a ridiculously small 2 billion years ago because of some initial hiccups in some of the observations. Even at that time, even though we didn't have very good radioactive dating techniques, other techniques that do not rely on radioactive dating showed that Earth had to be at least 3 billion years old at the time. Now we realize that it's at least 4.5 billion years old, and probably really pretty much right around that age. The oldest meteorite specimens have grains in them that are 4.568 billion years old, which means then, based on the chemical composition and physical composition of those grains, we realized that those grains actually occurred really at the time that our sun was starting to form. So Earth is definitely not, say, 4.6 billion years old, but probably formed soon after our sun started forming. And we don't have any rocks on Earth nowadays older than about 4.4 billion years. But nonetheless, the idea of Earth being older than the universe was an initial hiccup in the so-called Big Bang theories. But this was resolved in the 1950s when astronomers realized that they'd been using the wrong calibration for those variable stars that they'd been finding in these galaxies. And in other words, improved observations made us realize that there are multiple types of these variable stars, and we were using a calibration that was for a different type of variable than the ones that were actually being observed. And we realized that these galaxies are actually much farther away than we originally thought, which means the universe is a good bit older than we originally thought. And that's when the age of about 15 billion years started becoming the main idea for the age of the universe. Now, and that had a large uncertainty. The uncertainty in that back then was about plus or minus 3 billion years. But nowadays it's much tighter than that. Right now we realize that it's about 13.79 plus or minus 0.04 billion years. It's incredible that we have that level of precision. Even 15 years ago, the idea of having that level of precision would have been seen as very, very ambitious. But anyway, this whole idea of the Big Bang predicts that not only should galaxies be rushing away from each other, such that the farther they are away from us, the faster they're going to be going. And in fact, it's going to be an equation called the Friedmann equation, which comes out of general relativity, that actually tells us how fast they should be going based on what distance they appear away from us, which can be calibrated with how bright certain so-called standard candles appear in them. And these all give us this realization that, okay, yeah, there should have been this beginning at a finite moment in the past about 13.8 billion years ago. Well, even when we didn't have that age, that led to some direct predictions, testable predictions. And one of these was that the so-called bang, so to speak, it wasn't an explosion in any normal sense, but really just the sudden expansion of space-time and the sudden creation of matter, that should have left an imprint on the background that should be visible everywhere in the universe if you look at the right wavelength. Well, they started looking at the right wavelength in the 1960s, and they found it. And it was a serendipitous finding as well, because it was found by people who were not looking for it, and then they realized there's this extra radiation that we just cannot get, this background radiation that we can't get rid of in our detectors. And it was right at that time that people reinvigorated an old prediction of this, that we realized, yeah, you've actually found exactly what has been predicted. And that pretty much put the nail in the coffin of people who denied the Big Bang, even back in the 1960s, with the exception of a very small handful of scientists. But one of the other big predictions of the Big Bang, which was specifically denied by other cosmological theories at the time and to the present day, is that galaxies should have evolved since the Big Bang. In other words, through the interactions due to gravity and mergers, galaxies should look very different, say, just a billion years after the Big Bang than they look now, because a billion years ago, after the Big Bang, they hadn't had time to merge with each other and for the stars to evolve from young hot stars into older, cooler, redder stars. Well, when you look deep in the universe with something like the Hubble Space Telescope, you're looking farther and farther back in time. So if you see an object that's, say, 10 billion light years away, that means that the light from that object's so far away that the light took 10 billion years to reach us, which means we are seeing that object as it appeared 10 billion years ago in the lifetime of our universe. Well, that's less than 4 billion years after the Big Bang. And guess what? Galaxies 2, 3, 4 billion years after the Big Bang, for the most part, there are some tiny exceptions. I mean, sometimes you'll have very deep gravity wells that cause formation to be much faster than normal, but for the most part, galaxies 2, 3, 4 billion years after the Big Bang look very, very different than galaxies appear today. And here's one of these really deep images taken by the Hubble Space Telescope, where just about every object in this image is a galaxy. The ones that aren't galaxies have these diffraction spikes because they're point sources of stars, and point sources of light tend to diffract around the supports for the secondary mirror in the Hubble Space Telescope. So that's a star, that's a star, that's a star, and I don't see any other stars in this picture. It looks everything else is a galaxy. Now, the bigger ones, these are ones that are more somewhat modern galaxies. They're only maybe 1, 2, 3 billion light years away. They're relatively modern. But the very tiny ones that you see all over the place in this image, these are some of the early galaxies, so-called galaxy chips, as my advisor when I was in the UVA astronomy department called them. Well, and he got that from his advisor. These so-called galaxy chips, that they haven't quite finished forming galaxies. They're in the process of interacting with each other through these violent gravitational mergers that result in these huge bursts of star formation. And when you look at the spectra of these galaxies, not only do the spectra show that they are very, very distant because the wavelengths have been stretched unimaginably into the infrared spectrum, but also they show that the composition, the stars are very different. You have a lot more dust, a lot more bright stars than we have in galaxies nowadays. So in truth, we realize that yes, galaxies and the universe as a whole has very definitely evolved over the past billions and billions of years. And theories contrary to Big Bang theories do not predict such a drastic evolution of the material in our universe. In fact, they specifically say that the universe should appear pretty much the same at all points in time. And then finally, if there weren't enough nails in the coffin for contrary theories, the cosmic microwave background radiation, that so-called that leftover afterglow from the moment of creation, it has exactly the spectral form that is predicted for it to have. In fact, this was made from data taken back in 1992, and these error bars are multiplied by a factor of 400 just so that you can see them. In fact, there's this nice story how when these people who had done this study and were responsible for this and who eventually won a Nobel Prize, George Smoot, John Mather, when they were giving a presentation back at the UVA astronomy department in the early 1990s, they simply showed the theoretical curve, and they said, yeah, we have the theoretical curve, and it matches the data points that are plotted. And somebody in the audience raised their hand and said, why don't you show us the data points that you've plotted with the error bars? And the guy said, we did, but the error bars are much less than the thickness of the curve that we use to show the theoretical data. So it was an incredible confirmed prediction, and the actual temperature of this also gives a very nice, just the temperature by itself gives a nice estimate of the age of the universe when you realize the reactions that occur and just apply some simple thermodynamics. This shows that the universe is on the order of about 13 to 17 billion years old just based on this temperature. And of course now we have much more refined and precise estimates of the universe's age. Now, time to get back to the physics. So Newton's law of universal gravitation. So Isaac Newton, we've already talked a good bit about Isaac Newton before when we talked about Newton's laws of motion. Well, he also came up with a law of universal gravitation, and he showed using calculus, which he invented along the way. Wouldn't it be nice to just invent your own field of math when you can't solve a problem? Well, that's what Isaac Newton did. And he showed that the force of gravity of one object acting on another object is directly proportional to the product of the masses of the two objects and inversely proportional to the square of the separation distance between the centers of the objects. And I should mention here that Newton's law of universal gravitation has been superseded by general relativity, but nonetheless, when you get down to the levels of predictions that are made by Newton's law of universal gravitation, the equations of general relativity do reduce to Newton's law of universal gravitation, which in vector form looks like this. Don't copy this down. We're usually just going to use the magnitude of this, but the force vector equal to the product of the masses divided by the square of the separation distance between the centers of the objects, and then times this constant, which we call Newton's gravitational constant, which has this value down here. And this r hat is simply saying that the direction of the force is along the same direction as the separation of the objects. In other words, if you were to stop the motions of the planets around our sun and just look at Earth and Sun, then the direction of the gravitational force would not be in some random direction. It would actually be in the direction of our sun, from Sun to Earth. And this minus sign tells you that the force is attractive. Now, we're usually just going to deal with the magnitude of this, so we're just going to say F equals this big G constant, which is that 6.674 times 10 to the minus 11 SI units constant that you saw, times the product of the masses divided by the square of the separation distance. So this tells you that if you double one of the masses, the force becomes twice as strong. If you multiply one of the masses by x, then the force becomes x times as strong. However, this inverse square, what that tells you is that if you double the distance, then the force becomes 1/4 as great. If you triple the distance, it becomes 1/9 as great, etc. So this is a really remarkable result that Isaac Newton got by calculus. You can also get it by geometry as well through some ingenious geometric arguments. So, back to one of the earlier questions in the unit. What is the origin for the centripetal force of the roughly circular motions of planets around the sun? And that is gravity. It's mainly our sun's gravity, but it's really the gravitational interaction between the two objects. So, think about it this way. If you write down the equation for the force of gravity between two massive objects, that's Newton's law of universal gravitation. And the equation for the centripetal force on a body of mass m, moving at tangential velocity v and radius r, well, which m? Well, that's going to be the mass of the object that's actually moving, not the mass of the central object. So we're going to pretend for now that our sun is not moving. So like in the case of this, when this girl is swinging the ball around to figure out the centripetal force, you don't use the mass of the girl, you use the mass of the ball. So going down here and doing that, we say, okay, there's the equation for the force of gravity. There's the equation for centripetal force. Well, force of gravity is centripetal force for objects in orbits. So just set those equal to each other. And when you do that, I'll let you go through the math yourself. When you do that, those little n's, in other words, the mass that's swinging around those, cancel. And when you solve for v, you get v equals the square root of gm over r. So if you want to know how fast an object would be going in a circular orbit around, say, Earth at some certain distance, well, you plug in the distance from Earth's center down here in r, you plug in the mass of Earth up here, or the mass of whatever object is causing the gravity, and plug in the value of big G, and let the calculator do the math. Make sure you have parentheses in proper places, and then you'll get the speed at which the object is moving. Now, let me show you another very, very useful equation. So, how about another equation with relating Newton's law of universal gravitation with centripetal force? Well, remember another equation for centripetal acceleration. Instead of v squared over r, if you plug in v equals 2 pi r over t, then you get 4 pi squared r over t squared for centripetal acceleration, which you should have that equation memorized. So, well, cancel the masses just like before, and the little masses, that is, and you have this. And then, if you multiply both sides by t squared, and both sides by r squared, and divide both sides by gm, you get this. T squared equals 4 pi squared r cubed over gm. And that is Kepler's third law. Except now it's on a firm mathematical footing, where instead of having to set it up as a ratio, well, you can see how you could set it up as a ratio. If you keep the mass constant, and you're just comparing two objects orbiting around a star or sun of the same mass, then you say, okay, yep, t squared is proportional to r cubed, or as we would call it, a cubed in the truly correct analysis of this. So this is a really important result. It shows why. So Newton's law of universal gravitation, it's actually more of a theory than a law, and that makes it better, because it shows why Kepler's laws are the way that they are. In fact, if you apply calculus in full, not only would you obtain the correct equation for Kepler's third law, where this is a semi-major axis and this mass is the sum of the masses. In fact, when we use it, we're going to use the sum of the masses down here. Not only would you obtain the correct third law for Kepler, you would also obtain Kepler's second law, which is really a result of conservation of angular momentum, which we'll discuss in a future unit. And you obtain the first law. You end up solving a differential equation, and you get the equation of an ellipse, which is really quite incredible. And this shows us why the planets orbit around the sun in the way that they do. In fact, Newton's law of universal gravitation is one of the most important equations in all of science. It also shows why stars form, how stars form. So if you take a large, basically you can just use Newton's law of universal gravitation and use a little bit of calculus and show that if you get a large enough cloud of gas and dust, eventually its own self-gravity will cause it to collapse. And this is exactly what's going on in a lot of cases in places like the Orion Nebula, where parts of this gas cloud have collapsed and they have formed stars, which you might not be able to make out, but there are these 4 huge stars in the center of this image. They're called the trapezium cluster. Each star is about 20 times our sun's mass or so. And they were the first to form in this whole space, but there are actually a good 1,200 other stars in this nebula that we've found as well. Most of them are quite faint, and you need an infrared telescope to see through the dust. And something similar is going on in a whole lot of other places in our galaxy that we can see and observe with telescopes as well. The Eagle Nebula is a very famous one. In fact, you might already recognize this particular part of it, because when you reorient it and look through a different filter, in other words, the Hubble Space Telescope's filter, you get this, the famous pillars of creation. And we realize that in these little fingers, you actually have stars that are just now forming due to the mutual gravitational collapse of different parts of the dust and gas cloud. And really, it's not all that hard to do that analysis. What you simply do is you balance the inward pull of gravity from Newton's law of universal gravitation with the outward push of the gas pressure from the temperature of the stuff that's heating up, and you derive something called the Jeans mass and the Jeans radius, which just tells you how much of this stuff is required to cause a star to collapse. And you find that a typical giant molecular cloud like the Orion Nebula is eventually going to form typically on the order of about 1,000 stars or so. And another nice zoom in of this, and you can even zoom in on some of the objects that are forming. For example, this right here is a little tiny star with leftover dust around it. Well, what's going to happen with that dust? It's in the process of making planets. And we've seen this process in action a number of times, and you can do that. This is also something that people analyze using Newton's law of universal gravitation as well as other laws of physics to analyze the formation of planets. And you realize that due to conservation of angular momentum, you get these dust disks which collapse and form planets eventually. And well, not so much collapse, but the little particles in them end up colliding and form larger and larger objects. So we've seen these disks in various levels of formation. In fact, a very nice recent image from an infrared telescope. No, take it back. This was from a radio telescope, I think, from that observatory in South America. So where you have lots and lots of radio telescopes grouped together, but you find that not only do you have this protoplanetary disk around this newly formed star, but you have areas that have been carved out by newly formed planets. And you have a bunch of these things, like, let's see, 1, 2, 3, 4, 5, 6, 7. And probably more than that as you go farther and farther out. And this is a system that's a good bit larger than our own solar system, but nonetheless you can see the process in action. We've seen these types of things around other stars as well, so in some cases just a few of them. And in some cases we've actually visibly imaged planets. I've mentioned that we've discovered thousands of these things, but usually it's been through something like where we see the star's light dim in regular intervals as the planet passes in front of the star, or using the Doppler effect, we analyze as the star goes back and forth. But in some cases we actually have seen the individual planets themselves, which is a truly incredible time in the history of science that we're observing these things now. And in a lot of cases, you have to block out the light of the star itself to even have a prayer of seeing some of these things, but you can sometimes see them directly nonetheless. And some of these objects, as I've mentioned, they are in their star's habitable zones. Kepler-22b is a recently discovered object that's a good bit larger than Earth, but it's in its star's habitable zone, and so there's a good chance that it actually has liquid water on its surface. I say a good chance because water is a very, very common substance in the universe. It's one of the most common substances in the universe. So pretty much any star-forming region is going to at least start off with water. In some cases, the star's just so incredibly hot that it breaks apart all those water molecules very quickly, but in a whole lot of cases it's not. Those really hot, really big stars are really rare in today's universe. They were very common a few billion years after the Big Bang, but nowadays they're pretty rare. A galaxy isn't going to have all that many of them compared with the number of relatively cool stars like our sun that it has. Now, back to calculations. You can do things like derive the period of motion for Earth's moon using Newton's law of universal gravitation combined with a centripetal force equation. And I'll just kind of leave this calculation up here, realizing that gravity is the source of the centripetal force. So you have the centripetal force equal to Newton's law of universal gravitation, and if we want the period, then we're going to need to use an equation that has period in it. And we know the distance of Earth's moon from the sun. That's in your packet. In fact, a whole lot of these things like big G, mass of Earth, mass of sun, radius of Earth, radius, all that information is in your packet at the beginning of the problems that involve these types of concepts. So you're going to use the equation for centripetal acceleration that has both r and t in it. In other words, a equals 4 pi squared r over t squared, and solve for the period t. List your givens. And then, so you write the formula for universal gravitation on the left and formula for centripetal force on the right. And when you do that, here's what you have. And again, you use this one because it's the one that has r and t in it. They're asking for period, and we know r. And again, the mass of our moon cancels because it's in both equations. It's what's being swung around, so the motion should be described by what creates the big gravity well, which is Earth. So then you plug in numbers, and you solve for the period, and you get this many seconds, which you can't really see it down below here, but it becomes 27.5 days, or 2.38 times 10 to the 6th seconds. Now, if you were to have a question of the day over this stuff, hint, hint, nudge, nudge, wink, wink, then I would strongly recommend making sure that you have all of these steps in there. Because this is, and again, you can't see it down here, but this is the number with units and everything, so that's where this check and that check go. The number with correct sig figs and units. Now, another one, how about the velocity of Earth as it travels around the Sun? So, set centripetal force equal to universal gravity, and use your givens from the data sheet, which would be given to you on such a QOD if you were to have one, hint, hint. And the equation that you're going to need for centripetal acceleration this time is going to be the one that has both r and v in it, because we have r, we know Earth-Sun distance, an astronomical unit, 1.5 times 10 to the 11 meters, and they're asking for velocity, so the centripetal acceleration equation with both r and v in it is v squared over r, so that's what you plug in. And you do that, cancel things that cancel again, and what's left over, after all, is the massive Sun that primarily is responsible for creating Earth's orbital motion, as well as Earth's tangential velocity, of course. If Earth had no tangential velocity, we would crash into the Sun. And then, when you work that out, you get tangential velocity of 29,800 meters per second. So, I'll let you go through the rest of these on your own in the PowerPoint that's on the website, and that's all for this presentation.